Okay, good afternoon slash evening, everyone. I'm recording this around 6 p.m. in the afternoon or evening. I think it's pretty much evening at this point. It's now time for linear algebra video number 5. Okay, and in this video we're really going to be discussing quite a few things. So we'll talk about what it means for a matrix to be invertible. So something that you've probably seen at A levels or equivalent is the idea of a matrix having an inverse. Okay, and we'll mainly talk about, well, we'll define what it means in general for a matrix to be invertible. We'll mainly be talking about 2x2s because they're relatively simple, as you'll see, to deal with. We'll also sort of talk about some other things. We'll prove a couple of facts about some properties that inverse matrices have. We'll also have a look at the very end at a special sort of family of matrices, which effectively form what we call the standard basis for the set of m by n matrices. Okay, and then we'll basically prove a very interesting result at the very end. Okay, but let's just get straight into this. Okay. As always, if you do want to read up on this, these notes are basically all taken from Oxford's Linear Algebra 1 Prelims, which is effectively the same as first year course. And you can find this if you go to courses.maths.ox.ac.uk. Okay, without any more dilly-dallying, let's get straight into it. Okay, so linear algebra. Linear alg, hashtag 5. Okay, let me also just give myself some borders. I realize that's massive. That writing there is massive. I'm going to have to zoom in a little bit more. Linear 5. Okay, perfect. Okay, awesome. So there we go. Let's zoom in on that. Linear algebra number 5. Okay. So let's start off with the definition. So let A and M be matrices. Okay. By now you should obviously have an intuition about what a matrix is, so that should be fine. We're going to basically, well, as we know from the last video, matrix multiplication is non-commutative. So it means that if I'm multiplying matrix M by matrix A, and I'm not going to get the same result as if I multiply matrix A by matrix M, right? So the order of multiplication matters. This is not true in arithmetic, but it is true in linear algebra. So that's one of the concessions that we have to make. Okay. So what we can say is that pre-multiplying, so we have this term effectively for the two different variations of multiplication. One of them is called pre-multiplication. So pre-multiplying M by A means forming the product AM, right? Effectively, because pre-multiplying M by A. So the pre there is representing the fact that I'm placing the A before the M. Okay, so this is basically representing the matrix product AM, okay, which is not the same in the most general case as the matrix product MA. Okay, those two things are not the same. It is sometimes the same. Okay, we'll actually see what it means when it is the same a little bit later today. Okay, but for now, just this concept of pre-multiplying this matrix M by another matrix A effectively just means I'm forming this product AM, matrix product. Okay. So we also have another term for the other configuration, which is post-multiplying, right, which makes into intuitive sense. So post-multiplying, right, M by A, means effectively forming the matrix product MA, sorry. Okay? And sometimes what people might say is, for the first case, pre-multiplying is effectively the same as multiplying on the left, right? So you might hear that term. So multiplying on the left. So multiplying M by A on the left, but effectively, you probably get what I mean, hopefully. And then the second case, people might say it's multiplying on the right. But the main idea here is that you are aware that those two things are not the same, okay? AM and MA, in the most general case, with two matrices MA, are not the same, okay? So, because matrix multiplication is not commutative, okay? So you need to, whenever you're writing about matrix multiplication, you sort of need to specify, whenever you say I'm multiplying matrix M by matrix A, you need to specify in which sort of direction you're multiplying the matrix M by A effectively. So it's either on the left or on the right. I know in my video yesterday I didn't, but you can also typically infer from context. But realistically, you should, if you want to be precise, you should. And if you do see these terms, at least you understand what they mean. Okay, so it's still worth mentioning. Right, so let's move on. So in general, we write this matrix A squared to mean the matrix product AA. So you're multiplying a matrix A by itself. Okay? And notice, by the way, that this is actually only possible if A is what we call a square matrix. I'm not sure if I introduced that concept in a couple of videos, in any of my videos. I think I have, because they had it in the notes, so I'm assuming they mentioned it before. If not, all it means is just a matrix of the form n by n. So it has the same number of rows as it does columns. So A has to be of this form. Suppose that it wasn't of this form. Let's prove it, just very briefly. Suppose that it wasn't of this form, so that means that it's of the form n by n, right? It's a most general case. Well, then if we try and multiply it by itself, we're going to have this problem. The product doesn't even exist, because n and m, we obviously need to suppose that n is not equal to m, otherwise we just get this case up here, right? But if m is not equal to n, then effectively this product doesn't even exist. So it's basically only possible to even define this notion of the square of a matrix, a squared, if effectively a is a square matrix or is n by n. That's probably why we call it a square matrix. Actually, no, also because obviously it has n squared things inside it. But yeah, effectively the matrix product a squared existing, well, it exists if and only if a is n by n, right? There's no other, those two things are equivalent, right? So you wouldn't be able to have it existing, but a not being n by n just wouldn't be possible, right? As we effectively just shown. Obviously you can write it out more rigorously, but just for the sake of argument, hopefully you understood what I mean. Right. In general, so obviously we love to generalize in maths. In general, and it'll be useful to have this definition. So in general, if n is a positive integer, then we write a matrix A to the power of n to mean effectively A multiplied by itself n times, okay? So effectively the same as what it means to raise like a number to the power of, oh, sorry, just got a message from my teacher. Effectively, it's the same thing as what it means to what it means to raise, for example, 2 to the power of 6. You're just multiplying 2 by itself 6 times, right? The same is true with raising the matrix. We're raising a matrix to the power of n, where n is a positive integer, okay? Obviously, for numbers, we also have other types of powers, but for now we're not going to deal with those with matrices. But the most simple type of sort of power that we can have is a positive integer power, and this is what we're defining it to mean ultimately, right? This is just a definition, but it makes intuitive sense, and it's also a useful definition for a couple of reasons. The first, actually, before I say why, it's also probably important to know that a to the power of 0 is the identity matrix. Okay, so this is just a definition. Okay, obviously for numbers, right, for like a real number, itself raised to the power of 0 is always going to give you effectively 1. Right? Now, it kind of is the same idea with matrices, except we've chosen the identity matrix, okay? So actually it sort of has this matrix 1, 0, 0, 1, or 1, 0, 0, 0, 1, 0, 0, 0, 1, etc., right? In general, right, if A is a square matrix, then itself raised to the power of 0 is just the identity matrix. It's just a definition. Yeah, that's just the way that we've chosen it effectively to be. Okay, in the way that, I guess, it makes, the way that makes sense. Because what we also have in general for matrices A, well, just for a square matrix A, is that a to the power of m multiplied by a to the power of n is indeed equal to a to the power of m plus n. So these indices effectively rules, or at least this indice rule that you probably learn in year 7 for like numbers, right, is effectively transferable to matrices. Okay, so this, so that's like why this definition is really good, right? Also, I guess you could use it, right, to basically motivate that choice of a to the power of 0, right? Because if we want this to be true, effectively, for all positive integers and 0, mn, then effectively you would need to have a to the power of 1 times a to the power of 0 being a to the power of 1 plus 0. And since this is just the identity matrix, then that will be true, as we saw yesterday. Okay, so effectively, I assume that it's just a to the power of 0 being the identity matrix is just a very convenient choice because it allows this to be extended, probably for many other reasons as well, right? But for now, it's just a definition, right? It's just a choice that we're making. But this comes out of that, right? I mean, it's pretty simple to see anyway, because effectively you just have a m times, and you're multiplying by itself n times, and you're combining them into a string of length m plus n, right? So that's basically all that's happening in this scenario. Okay, now there's another sort of interesting thing that we can do that, probably doesn't, you might have thought of this. Honestly, there's probably some quirky videos online which really do this kind of thing. But in general, right, this is sort of not really spoken about, at least not in A-level, I don't think. But it's an interesting concept, right? So if I give you a polynomial, so given a polynomial, we have a general form for a polynomial, so p of x is equal to, so some coefficient multiplied by x to the power of k, add another coefficient x to the k minus 1, add blah, 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 all the way down to a1x plus a0, right? So given this polynomial, we can actually define the polynomial evaluated with a matrix input, right? So I can basically, if I have, for example, x squared plus 2x plus 1, I can plug my matrix as an input value into that polynomial. It's slightly weird, but it's actually interesting, right? Because then maybe you can I mean, this would definitely be useful, I assume, later on. And it's just an interesting concept to think about, right? That you can effectively now transfer these polynomials that you've been dealing with, probably for a long time now at this point, into sort of linear algebra, and you can plug matrices into them, right? Because you probably didn't think, at least not intuitively, that matrices are compatible with these sorts of polynomials, right? But they are, right? And so there's lots of interesting stuff that can go on there. Okay, so we define the polynomial evaluated sort of at a matrix, so with a matrix input, to basically mean, well, you just basically replace all the x's with the matrix, right? Because now we know what the matrix raised to the power of an integer is, right? Or a positive integer, right? So effectively, it literally just means, so if we wanted to evaluate the polynomial with a matrix input, then effectively we just get the sort of exact same polynomial, right? But just with all the x's, which would typically be numbers, replaced with matrices, or the matrix that you want to basically input into your polynomial. And also the other caveat with this, though, is obviously typically we have plus a0, right? a0 is just a coefficient, so it's just like a real number, or even a complex number in some cases. But effectively, it doesn't really make sense to add a matrix and a scalar, right? You can't really add a matrix and a number, so you need to effectively scale this number by the identity matrix to basically make this addition process make sense. And obviously the identity matrix also needs to have effectively the same dimensions as A, which will be a square matrix since we're raising it to the power of things. Okay, so A is going to be a square matrix, and so therefore it's of the form n by n. So we can just choose the n by n identity matrix to be input here, right? And that works obviously for all values of n, because A could be 2 by 2, 3 by 3, even 1 by 1 if you want, right? That's not particularly interesting. Okay, and so on and so forth, right? With positive integer n, effectively. And so this is what it means, right? To evaluate a polynomial, using a matrix as your input value, which is kind of weird but pretty cool, right? And I think if you are interested in that, you can definitely explore it further. Though we won't really talk about that anymore, though it is introduced at this point in time. We won't talk about it anymore in today's video, but it will definitely, I think, come up later on. So at that point, it will be useful to know. Okay, right. So now here's a couple of things that effectively we can prove, okay, with our current knowledge of matrix algebra and things like that, right? So first one is a claim. So if and it's sort of a seemingly random claim, but the purpose of these two sort of claims will make sense after I've sort of covered them. So let sort of this matrix A be a matrix of sort of trig functions. So it's a matrix given by, so literally like looking like this. So cosine alpha, sine alpha, and minus cosine alpha, right? So this is your matrix, right? And it basically just has these trig functions inside it, right? Okay, that's perfectly fine, right? Because effectively, if you give me an alpha, right, and you probably only really, we'll just assume for now, although it doesn't necessarily have to be the case, you can extend trigonometric functions to take complex inputs, but let's now assume that the input is a real number, then, this just spits out another real number, right? Just sine and cosine, they're just functions that spit out real numbers for given values of alpha. So if you give me an alpha, I can plug it in and just find what this matrix looks like. But actually, we don't even need to do that in this case because we're dealing with the most general case, just like this. The claim is effectively that a squared is always equal to the 2 by 2 identity matrix for all alpha. So this symbol here means for all, okay? So for all alpha that we care about, okay? So in this case, just real numbers, okay? Obviously, I think this will also work for complex inputs if you were to extend the function. But yeah, I mean, primarily just you can think about this as alpha being a real number for the time being, because we don't really care about that, right? That's not the point. So let's prove this, right? So obviously we need to prove it. So a squared is obviously just going to be cos alpha, sine alpha, minus cos alpha, and then you obviously just multiply it by itself. So cos alpha, sine alpha, minus cos alpha. Okay, now we just do the typical thing. So obviously we dot the first row of this with the first column of this, right? So that just gives us cos squared alpha plus sine squared alpha, and then you do the same thing. And obviously this, and if you do it, you'll get cosine alpha sine alpha minus cosine alpha sine alpha. So that's 0. This will be 0, and this here will be sine squared alpha add minus cos alpha squared. So just add cos squared alpha. Okay, so this is our resultant matrix, right? And clearly, for all values of alpha, cosine squared alpha plus sine squared alpha is just 1. So this is indeed, as we would expect, well, as the claim is telling us, this is actually the identity matrix, right? 1, 0, 0, 1, which is just simply I2, the 2 by 2 identity matrix. So I'm going to specify its size in this case as a 2 by 2 matrix. Okay, that's actually it, right? There's not much more to it than that. What am I doing? There's not much more to it than that, right? But it's interesting that we have this matrix, and we have infinitely many of these sort of matrices, and effectively, whenever we square them, we always get the identity matrix. So if I was to think about this notion of a square root, right? Because obviously when I have, for example, numbers like real numbers, for example, let's take 4, right? Obviously the square root of 4 is 2. Okay, but what does it really mean to take the square root of a matrix? Well, it kind of just, you could think of it as just reversing this process, right? So if I take a matrix A and I square it, I get the identity matrix. If I were to square root the identity matrix, then in theory, A, in other words, this matrix should come up. But the thing about that, though, is that actually there's infinitely many different matrices here, right? Because alpha could be any real number. There's infinitely many real numbers. So there's infinitely many A, right? Which means that if I were to try and take the square root of the 2 by 2 identity matrix, there would be infinitely many possibilities as to what it could be. Right? And I'm assuming that these are not the only, like this family of matrices here is not the only possibility. So, I mean, that might be wrong, but I assume that that is the case, right? That's not true, right? That the square root of the 2 by 2 identity matrix would not just be this family of matrices, right? There's probably going to be other things as well that give you the identity matrix when you square them. So it's a much more complicated matter to deal with the square root of a matrix because infinitely many matrices square to give you the 2 by 2 identity matrix. So, yeah, that's basically kind of the point of these two claims, okay? The next claim is a little bit more interesting, though. Let me do it over here. So our claim... So the claim is effectively, if I give you a matrix, so define a matrix B to be given by 0, 1, 0, 0. So a pretty simple matrix, right? Almost as simple as you're going to get, other than like the zero matrix, etc. So a pretty simple matrix, but the claim is that there is no matrix, there is no matrix C, okay, with real or complex entries, so literally like no matrix pretty much, with real or complex entries, right? Such that when you square it, you get B. So if I were to talk about square roots again, coming back to the idea, then there is literally no, and I wanted to find the square root of this matrix B, again, I would arise at a problem, because there actually is no matrix, as we'll see, that actually squares to give you B. So, yeah, there's a couple problems here. So there could be infinitely many matrices that square to give you a given matrix, or none, right? So there's a big problem here, like with square roots of matrices, right? It's not as simple as just taking the square root of a number, unfortunately. So we need to be careful. But yeah, okay. Let's now prove this, right? So, proof, right? So assume that, there is a matrix C that basically squares. Sorry, my teacher's again saying an assignment. Assume that such a matrix C exists. So suppose that C exists, right? We're trying to prove it doesn't, such that obviously C squared is equal to B, right? C is a matrix, okay? Well, already, the first thing that we know is that obviously for C to be raised to some positive integer power, C must be n by n. So C must be a square matrix, so C must be a square matrix. We can actually ascertain specifically what its dimensions are, because B is a 2 by 2, right? So the only way to basically have an m by n multiplied by an m by n, which gives you another m by n, okay, because of this, the first and the fourth here, is the only way to get that being a 2 by 2 is to have n is equal to 2. So actually C must be a 2 by 2 matrix. So even better, so C must be square, but actually C must be a 2 by 2, okay? So now we know some information about it. So let's C equal A, B, C, D, like this, a 2 by 2 matrix, just general, with values A, B, C, and D inside it, or components A, B, C, D, whatever you would like. Okay, so C squared, right, that's just going to give you A, B, C, D multiplied by A, B, C, D. And when you actually carry out this calculation, which is matrix multiplication, like you just do the algorithm effectively, what you're going to get is effectively A squared plus BC, B times A plus D, right, A squared plus BC, AB plus BD, right? Yeah, perfect. C times A plus D, and BC plus D squared. Okay, so this is the square of C. That's just C squared for any arbitrary 2 by 2 matrix C. I'm gonna have to extend these boundaries, otherwise I'm gonna go wild. Okay. Let me just extend these. Extend. Okay. Right, yeah, so for any 2 by 2 matrix C, this is what the sort of C squared is going to look like. Obviously, you want that to equal 0, 1, 0, 0, right? If C exists, this has to be true, right? So what that means, so we can equate each of the components of our C squared matrix. So A squared plus BC, it has to be equal to 0, right? B times A plus D has to be equal to 1, right? C times A plus D has to be equal to 0, and BC plus D squared has to be equal to 0, right? Okay, so let's start by looking at this. So obviously this being equal to 0 obviously implies either C is equal to 0 or A plus B, or A plus D is equal to 0. Right. Well, if A plus D is equal to 0, then we already can arrive at a contradiction. Because if A plus D is equal to 0, then this left-hand side here is 0, which is not 1. So A plus D cannot be equal to 0. So C must be equal to 0. Now, because C is equal to 0, this first effective criteria becomes A squared plus 0 is equal to 0. So A squared equals 0, which implies that A is equal to 0. Right? Similarly, this last criteria becomes D squared equals 0, which implies obviously that D is equal to 0. Okay? So we get that both A and D are 0, right? and so, but then that's again that we then arrive at a contradiction again, right? Because then this left-hand side here becomes b times 0 plus 0, which is just 0, which is not 1. Okay, so no matter what, right, we're never going to have all of these criteria satisfied at once, because if the third criteria is satisfied, then effectively the second one is not, right? And so, yeah, and if the second one is satisfied, then effectively the third one cannot be satisfied, right? Well, effectively, the idea is just that the third one can never be satisfied, right? So if the third one were to be satisfied, it would lead to a contradiction. So it can never be satisfied. So all of these can never be satisfied because one cannot. That's the effective point. Yeah. Okay. Okay. Awesome. Right. So that's the proof, right? So effectively, what we're saying is that therefore C does not exist. So C does not exist. Right? Contradiction. And that finishes the proof, right? Then we're done. Right, so now let's move on. Let's consider now a system, a linear system of equations, right? So we kind of delved a little bit into these at the very beginning. But now let's just consider a very simple system of two simultaneous, just the system of simultaneous equations. Of effectively, we're going to consider a system of two linear equations in two real variables. Right? So effectively what it will look like is it will look something like this, right? So you'll have ax plus by is equal to, effectively we'll say e, and then cx plus dy is equal to f. So that's 1 and that's 2, okay? So we can algebraically solve this system, right? We don't even need to use any linear algebra, right? We can just use arithmetic and like standard algebraic techniques from secondary school / high school, right? So if I multiply 1 by d, then what do I get? I get adx, adx plus bdy is equal to ed, right? And if I multiply 2 by b, what do I get? I get cbx plus bdy is equal to bf. So immediately I can subtract these two things, and that gives me adx minus cbx is equal to ed minus bf. Okay, so I can factor out the x and divide to simply get that x is equal to de minus bf divided by, effectively, ad minus bc. Okay, so I've solved for x, and effectively you can just plug this value back in. Okay, just plug and play effectively. Just plug this value back in, finish off the algebra, right? And what you're going to end up getting is y is equal to af minus ec divided by ad minus bc. Okay, so same denominator but different numerator. Okay, so this is just a general solution, nothing very interesting here, right? Just general solution to this to any system of two linear equations in two variables, right? Basically, yeah, right. And we can consider these to be real variables as well, so just real numbers, but I guess that doesn't necessarily have to be true. But you know, like, there you go, right? So we've solved it algebraically, but what is really the point, right? What are we doing here, right? Why does this even matter? Like, why have you all of a sudden moved from effectively this idea of a square root of a matrix, and now all of a sudden talking back about these linear systems again? Specifically, this sort of system of two linear equations in two variables, right? I'll get back to that. I'll answer that question in a second. But the first thing that I want to sort of highlight is that obviously, you know, what is going to happen, right? In this specific case, right? Because we have a fraction here. There's one case where fractions are problematic, and that's when the denominator is 0. Okay, so if ad minus bc is equal to 0, then what happens, right? What does that really mean? Well, let's think about this geometrically, right? Because that's one very interesting way of thinking about this. Both of these, hopefully you'll agree, represent lines, right? Both of these equations in the xy plane, standard Cartesian plane, they represent lines, straight lines. Okay, this is the equation of a line rearranged. Okay, or I mean, this is the equation of a line. I say rearranged because most of you might have seen it, including myself. Obviously, probably have seen it in secondary school as y equals mx plus c or some equivalent. You probably also have seen this, but I say rearranged because you might think that the other one is more common. But effectively, it's still representing the same thing, right? It's still representing a straight line. So both of 1 and 2 are straight lines geometrically in the xy plane, and their gradients, respectively, are minus a over d. So that's going to be the gradient of this line, so gradient of 1, right? And the other one, if you just compute it, is going to be what? It's going to be minus c over d, right? So minus c over d is equal to the gradient of number 2, right? And obviously, for these lines to be parallel, as you've hopefully learned in secondary school, they need to have the same gradient, right? So no matter what I do to them, they need to have the same gradient. So they don't and they could be on top of each other, right? Which is also parallel, but they don't necessarily need to be, okay? They just need to have the same gradient, right? So if minus a over d is equal to minus c over d, why have I written d here? I think that's wrong, isn't it? I mean minus a over b, right? Not minus a over d. Minus a over b right? So if minus A over B is equal to minus C over D, then you can get rid of the minus signs, right? That's fine. And you get AB is equal to CD. Or equivalently, AB minus CD is equal to, oh, sorry, no. Oh my goodness, my algebra, man. Of course, that's not what I mean. I mean AD is equal to CB, right? Or BC, right? Same thing with real numbers, right? The real multiplication of real numbers is commutative. So AD, this is equivalent to me saying that AD minus BC is equal to 0, right? And so these two lines being parallel effectively is the same as it's equivalent to. You can go the other way as well. AD minus BC being equal to 0. So when we ask what does it mean for AD minus BC to equal 0, it effectively means that those two lines are parallel. And if they're parallel, well, clearly there's going to be either 0 solutions, right, if they're like this in the xy plane, right? So we're just considering 2 dimensions here. In the xy plane, there's going to be 0 solutions, or there's going to be infinitely many when they coincide. Okay, so there won't be a unique solution. Okay, so there is so this implies AD minus BC equals 0 means that there is no unique solution. It means no unique solution. Okay, it doesn't necessarily mean no solution because you also have the case where they overlap and you get infinitely many. But it means there won't be a singular solution, right? And you can think about that geometrically. Okay, so that's a very interesting thing that we need to note now. Okay. Because naturally it comes up, right? Like, what does it mean when this denominator is 0? And you should always ask yourself that, right? Because sometimes that actually gives you meaningful sort of things, right? Like if you ask what does it mean for this denominator to be 0, and it actually gives you sort of one of the values that you thought solved an equation or something, and so therefore doesn't actually work, right? Then that would have actually changed your answer, right? So you need to be careful with denominators being equal to 0 in general. And in this case, they actually give us a very interesting situation, right? Which basically means that the simultaneous equation, the system of these simultaneous equations effectively do not have a unique solution in this case when AD minus BC is equal to 0. Okay, right. Equivalently, so what was all this about, right? Again, still haven't answered that question. Let's talk about it, right? Well, the following system, right? We can use matrices to represent it, right? And I'm sure you probably have seen this as well in further maths, right? At A level. So effectively, this is the same thing as me saying ABCD multiplied by XY is equal to EF, right? And so what we have now shown algebraically, because we solved for X and Y, is effectively that XY is equal to 1 divided by AD minus BC multiplied by the matrix D minus B minus CA, and then multiplied by EF. Okay, so this is effectively what we have just shown, right? Because we solved for XY, and if you do this sort of matrix algebra here, you multiply these two matrices, you get DE minus BF, right? That's your first term, and you multiply that by 1 over AD minus BC, you get the exact same thing that we had for X over here, and the same is true for Y. So effectively, we've now sort of reverse engineered this system from this starting point here, where, we just have the system as it's given to us, to this point here, right? And so this is the linear algebra interpretation of what we've just done, okay? Fairly standard stuff, right? You've probably seen this in further maths A level, right? But it's actually very useful because this is where we start to talk about the inverse of a matrix, right? Which is a very important thing, okay? And I'm sure you'll have spoken about that at A level as well. Okay, right. So how do we really talk about this even further? Well, first things first, note, right, that this product, so we can take the product of these two matrices, D minus B minus CA, and ABCD, right? So where have I gotten this matrix from? Well, I've effectively just pulled it from the above line, right? It's just this matrix, okay? Without the scaled 1 over AD minus BC in front of it, and without this EF here, because that was only relevant when I was dealing with a system of equations, right? So whenever, just this product by itself, right, if you do it, then you'll see that what you get is as follows. AD minus BC, 0, 0, AD minus BC, right? And you can literally just do it right now. You can kind of already see that this is meant to be a D. Yeah, so AD minus BC, BD minus BD is 0, minus CA plus AC is 0, and then minus BC plus AD is AD minus BC, right? And so this thing is just the same, actually, if you just scale it, if you take out the factor of AD minus BC as AD minus BC multiplied by the 2 by 2 identity matrix, right? So in general, right, this product actually gives you AD minus BC multiplied by the 2 by 2 identity matrix, right? And also, right, you can verify this yourself, that effectively ABCD multiplied by D minus B minus CA also gives you the same thing, okay? So obviously, in general, right, matrix multiplication is not commutative, okay? But in this case, it is, okay? So this is an interesting case, right? Because one might naturally wonder what it means, right, when matrix multiplication is commutative, right? Like in which cases is it commutative? Okay, and clearly this is one of the many cases where it is. Okay, there are actually lots, but there's probably infinitely many cases. But in general, right, obviously it's not true, right? There's infinitely many more cases where it's not true. Okay, this is one of the cases where it is true, though, right? So that is very interesting. Okay, and it lends itself very nicely to effectively this discussion of the definition of an inverse, of what it means for a matrix to be invertible. But before we do that, I guess we can also just say, if A is this matrix ABCD, and B is a matrix given D minus B minus C A, and then you scale that by 1 over AD minus BC, right? Then we have this property that AB is equal to BA, so matrix multiplication there is commutative, and it gives you the 2 by 2 identity matrix, okay? Okay, now it's time to define the inverse of a matrix in general. Okay, so let A be a square matrix. So let A be a square matrix. So a square matrix just means that it's an n by n matrix. Okay, let A be a square matrix. Now we say, right, so we can define B to be an inverse of A. We say that B is an inverse of A, if, right, effectively, BA is equal to AB is equal to the identity matrix for the given value of n, right? Because A is n by n, it's a square matrix. And so effectively, whichever value of n that you're considering is going to be the same as the effectively size of this identity matrix, right? And it holds for all of the possible positive integer n that you can consider, right? So this is what it means, right? So B being an inverse of A effectively means that that multiplication is commutative, right? So that effectively AB is equal to BA, right? And that will always actually give you, not only is it commutative, but it will always give you the identity matrix. Okay, so if that is true, that BA is equal to AB is equal to the identity matrix, then B is an inverse of A. So in order to check and verify statements about inverses, we need to check that condition, okay? Because if that condition is not true, then we don't have the inverse, and then B is not an inverse of A, right? Okay. So, oh yeah, and also another thing that's probably worth mentioning is that any matrix that has an inverse is said to be invertible. Okay, so if a matrix itself has an inverse, not always true, right? As we'll talk about as well. If a matrix does have an inverse, then it's said to be invertible, and if it doesn't have an inverse, then it's said to be singular. Okay, so inverse has inverse means invertible, has inverse invertible, does not have inverse, no inverse means singular. Okay, these are two words that you need to now get used to. Okay, because they're going to come up again and again. Okay, right, so now let's prove a couple of theorems about properties of inverse matrices. Okay, so, okay. Right, first theorem is as follows, right? So if A is a square matrix, that is invertible, right? That is invertible, then it is unique. So the inverse is unique, right? And represented as a to the power of minus 1, right? And represented as a to the power of minus 1. Okay, so if A is a square matrix that is invertible, then the inverse is unique, right? That's basically what we're trying to prove, and it's represented as a to the power of minus 1. Right, let's prove this. Okay, so suppose that the inverse exists, right? So suppose A square and invertible, so A is a square matrix and it's invertible, right? So suppose that that's the case. Okay, but there are two inverses, right? So but B and C, with B not equal to C, are both inverses for A. Right, so suppose that we do have this sort of condition that A is a square matrix and it's invertible, but effectively its inverse is not unique, right? So somehow this is true, okay? Like just imagine it, that it were true, okay? Then then the matrix B is obviously the same thing as the matrix B times the identity matrix. We actually proved this yesterday, okay? We proved the more general form of it, but effectively it extends in general because since A is a square matrix, then if B was an inverse for A, then AB equals BA equals the identity matrix, right? And B can only commute with A both ways, effectively, if B is also a square matrix, right? And so effectively, yeah, we're going to have B commuting with the identity matrix, right? And so B multiplied by the identity matrix is just going to spit back B, right? Okay. So this is true. And the identity matrix in this case is actually the same thing as B multiplied by AC, right? Because since C is an inverse for A, then AC equals CA is equal to the identity matrix. Okay, so effectively now by the associativity of matrix multiplication, something we proved yesterday, we get that B times AC is equal to BA times C. And because B is also an inverse, right, for A, effectively BA is just the identity matrix. So this just gives us IC, which is the same thing as C, right? Because we also proved this yesterday, just the other way around, that the identity matrix multiplied by another matrix just gives space back itself if that product exists, which it does in this case for the same reasons as why it existed for B times the identity matrix, right? So effectively, if we just look back at what we've just shown, right, so we had basically like a long string of equality here, but effectively we've just shown that B is equal to C. So if there are two inverses for A, then they have to be the same. But that contradicts this, right? So that's a contradiction. Right? So inverse is unique, right? So then we're done. So inverse is unique. and equals a to the power of minus 1. That's just a notation as to how we write the inverse, right? This plus here also means and. That's just something that I do, but yeah. Okay, so the inverse is unique, and it equals a to the power of minus 1. That's just how we write it. It's a notation thing, that's fine. Okay, next, we have another theorem. We have a couple more. Effectively, this just tells us that the inverse, if I take the product of two matrices A and B, matrix product, as we discussed in the last video, and I take the inverse of that matrix product, it's the same thing as if I take the inverse of B and then multiply that by the inverse of A. Okay? Okay, so let's think about this, right? So why is it necessarily true? Well, I mean, we can pretty much just prove this by considering the product of AB and B to the minus 1, A to the minus 1, right? Both ways. Because if this is an inverse, so if this is an inverse, then this multiplied by AB is equal to AB multiplied by this is equal to the identity matrix, right? Okay, so let's just do it, right? Let's just literally take that, calculate that product. So obviously we need to suppose that A and B are invertible square matrices first. Suppose AB invertible square matrices so that effectively this product AB multiplied by B to the minus 1, A to the minus 1 is the same thing by the effectively associativity of matrix multiplication. So we can just move those brackets around however we want. Is the same thing as A multiplied by B times B to the power of minus 1 multiplied by A to the power of minus 1. Now, since B to the minus 1 is an inverse for B, right? Then effectively we can just write this as the identity matrix. So what you get here is A times the identity matrix times A to the minus 1. And from results that we proved yesterday, A to the minus 1, AI is just A. Just because A times A to the power of minus 1. Now since A to the minus 1 is the inverse for A to the minus 1 is equal to A to the minus 1A, which is equal to the identity matrix. Okay? So we have shown successfully that AB multiplied by B inverse A inverse is just the identity matrix, right? This is really just the sort of intuition for it, right? Like, because I mean, you might wonder like, how do we even get to this, right? This proof will work because we can just show that like it works both ways by definition and gives us the identity matrix. But how do you come up with it? And this is kind of you just reverse engineer it, right? Because intuitively you want AB multiplied by something to give you I, and you know that something, right? And obviously the other way around as well has to give you the identity matrix. You know that the identity, effectively the inverse is unique. Okay, so once we found it, and effectively you can see just by this, right, without even necessarily doing it, we want the B to cancel out to give us like the identity matrix, also the A to cancel out. So we have to multiply by B to the minus 1 first, so that we get this associativity working in, which gives us A times A to the minus 1, which gives us the identity matrix. Right, so you can see like why this is the case, like, and how you could technically reverse engineer this, though it's harder to do if you really wanted to. Okay, so let me also just move this down, right, and this as well. Okay, and the other way is also true, right? So you can just do it the other way around. So B to the minus 1, A to the minus 1, multiplied by AB, use associativity again, and you'll just show that it gives you I, right? And that's just the general idea. I mean, hopefully you guys see the argument that we used above. Use associativity, you get A to the minus 1A, gives you the identity matrix, right? Then B to the minus 1B, well, B to the minus 1I is just B to the minus 1. Multiply by B, you get the identity matrix again, as required. So this just gives you the identity matrix, okay? So, inverse of AB is just equal to B to the minus 1, A to the minus 1. And obviously from A inverse is unique, so we're done. Right, that is the only inverse. Okay? Okay, very good. All right, next claim is as follows. So this is a theorem. The theorem, well, all these are theorems. I say claim, but they're all theorems effectively. Is that A to the inverse of A, right, assuming it exists, the inverse of the inverse of A is just A, okay? So that's important, and it's actually quite simple to see, okay? It doesn't really rely on too much, right? So the proof is as follows. If A is, square invertible matrix, right? So just all the conditions we need for it to even have an inverse, that's defined, right? Then, sort of by definition, right? A times A to the minus 1 is equal to A to the minus 1A, right? Is equal to the identity matrix for whatever n that we care about, right? So A will be square, so n by n. Whatever that value of n is, the same as the size of the n by n size of the identity matrix that we get as a result of those products, right? Okay, so this is true in general, and if you just read it the other way around, you see that A to the minus 1A, right, is equal to A to the minus 1 is equal to I, right? So if I wanted to find the inverse for A to the minus 1, well, it's unique, okay? So we know that already from A, from the first thing we proved, right? And it just is A, right? You can just see that, because if A to the minus 1, any inverse for A to the minus 1 would have to satisfy our definition of the inverse, which is effectively that A to the minus 1 multiplied by the inverse of A to the minus 1 has to be equal to the inverse of A to the minus 1 multiplied by A to the minus 1 has to be equal to the identity matrix. You can see, though, that if you just substitute A in, then that works, right? Like, just by sort of inspection, right? Obviously, you can write that a little bit more formally if it was a proper proof, but just for the sake of argument here, you can see, therefore, so A to the minus 1 to the power of minus 1 has to be equal to A, right? So the inverse of an inverse just gets you back to where you started, okay? So that's quite interesting. Kind of like negative, negative, and negative gives you positive, right? So it just gets you back to where you started. Okay, so which implies inverse of a to the minus 1 is a. And obviously also inverse is unique. Okay. Yeah, and the inverse is unique, so we found it basically. That's basically the main idea. Okay, so now just a couple more theorems. So now this is not really about inverses anymore. Well, actually, it is about inverse. Sorry, this is about inverses, but it's sort of veering away from the properties of inverses, and we'll talk about what the inverse of a 2 by 2 in general is. Okay, so it's a theorem. So the matrix. So if I give you a 2 by 2 matrix, which is an arbitrary 2 by 2, A, B, C, D. So the matrix A, B, C, D, it has an inverse, right? Has an inverse, if and only if, right? So you got a double F there. Effectively, AD minus BC, right, is not equal to 0. Okay, and this quantity AD minus BC you may be familiar with. We typically refer to it as the determinant of our 2 by 2 matrix. Okay, so from A level probably further maths you've seen this, you've heard that term before, the determinant of a matrix. That's what AD minus BC is. Okay, and probably you also know that when AD minus BC is equal to 0, then your matrix is singular, right? It has no inverse. Okay, these are things that you probably learnt, right, in A level further maths, and they're coming back now. Okay, so the matrix A has an inverse if and only if AD minus BC is not equal to 0. Okay, and we can prove a 2 in 1 here, because it's not really hard to do so, that if AD minus BC is not equal to 0, right, then our inverse is actually given by 1 divided by AD minus BC multiplied by D minus B minus CA. Okay, so there we go, right? So this is basically the theorem that we want to prove. So here's the proof. Well, I mean, we already basically have seen this thing here, right? We've already seen this because when you multiply this by A, B, C, D, right, which we did before, you get the identity matrix, and the other way around is also true. So matrix multiplication commutes, and it gives you the identity matrix. So coming back to that, we now see that this is actually just the general inverse of a 2 by 2. Okay, obviously if AD minus BC is not equal to 0, right? So if AD minus BC is not equal to 0, then that is our inverse, right? And so that's also proven one of the directions of the above statement, okay? Precisely, it's proven that if AD minus BC is not equal to 0, then the matrix has an inverse, because we found it, right? We literally constructed it, so we know it exists. The only other thing we need to prove, actually, is that the matrix, so if the matrix has an inverse, then the determinant is non-zero, okay? So we need to show, I mean, you guys, I'm not going to write that because it just takes up time, but we need to show, effectively, that if the matrix has an inverse, then the determinant is non-zero, so AD minus BC is not equal to 0. Okay, that's all we need to do. So now let's suppose, right, that AD minus BC is equal to 0, right? So suppose that AD minus BC is equal to 0, right? Right, okay, so then, in that case, right, if I consider the matrix B, which is D minus B minus CA, right, so it's just this part without the 1 over AD minus BC in front, and I multiply it by A, B is such that, right, this matrix B is such that BA, right, is effectively the 0 matrix, okay? You can try that for yourself, but you are going to get it, right? Because in this case, AD minus BC is 0. So before, when you multiply BA, you're going to get AD minus BC multiplied by the identity matrix. But in that case, AD minus BC is 0. So it's just the 0 matrix, right? So BA is the 0 matrix, right? So suppose now that C is an inverse for A. Suppose that C is an inverse for A, right? And suppose that it exists, right? And it exists that it. Well, I mean, yeah, we're basically doing that, right? Suppose that C is an inverse for A, that obviously exists. Then, right, the 0 matrix is just the same thing as the 0 matrix multiplied by C. We also proved this yesterday, or in the last video. And the 0 matrix in this case is just BA. So BAC is just 0, the 0 matrix, right? And we can use associativity of matrix multiplication to give us that this is equal to B times AC, right, like this. Because matrix multiplication is associative, you can move the brackets around. And AC, because C is an inverse of A, AC is the identity matrix. So, and in this case, A and C, they're both 2 by 2, so it's going to give you the 2 by 2 identity matrix. Right, and anything B times the 2 by 2 identity matrix just spits out B, right? Gives you B back from the same thing that we proved in the last video. Okay, so B just is the 0 matrix, right? So since B is the 0 matrix, so B is the 0 matrix, which implies obviously that D minus B minus CA is just equal to all zeros, right? So effectively that just tells us that all of A, B, C, and D, they have to all be equal to 0. Okay, which is basically just crushing our matrix, right? And because that's true, then equivalently A. So the matrix A, which is equal to ABCD, is also the 0 matrix, right? So it's also the 0 matrix, right? So that effectively contradicts. So obviously contradicting the fact that AC is the identity matrix, right? So contradicting AC being the identity matrix, 2 by 2 identity matrix. Because if A is a 0 matrix, then 0 matrix multiplied by any other matrix just gives you the 0 matrix right back. Okay, so this cannot be right. You cannot multiply the 0 matrix by another matrix and give you to get the identity matrix. It's not possible. Okay, so it's a contradiction, right? And so therefore C does not exist. Okay, so right, so C does not exist. So this is how existence proofs kind of work, right? Because now, obviously, like if it doesn't exist, you can't like sort of continuously search for it. If it did exist, you could try and construct it, but if it doesn't exist, you have to prove somehow that it doesn't. Okay, and that is obviously you cannot search through every possibility, so you have to sort of use these sort of smart arguments to do so. Right? So C does not exist, and effectively we've proven. So if a to the minus 1 exists, AD minus BC cannot equal 0. Okay? Boom. Effectively, if this is true, then this cannot be false. Okay? So we cannot have a to the minus 1 existing, but AD minus BC being 0. It's not possible. Okay? As we've just shown effectively. Okay, so let's finish up by talking about sort of an interesting family of matrices, right? Okay, so first of all, I want to give you effectively just imagine that we have two positive integers, so capital I and capital J, between one lowercase m, and I think I meant lowercase n. Okay, so I is sort of between 1 and lowercase m, and j is a positive integer between 1 and lowercase n. Okay, so so we're going to use a matrix, we're going to define a matrix E, subscript capital I, capital J, right, represents, right, the m by n matrix, right, with ones in the ith row and the j column. So capital ith row and capital j column. So basically just a 1. It's really just a singular 1, right? It's just one position. With 1 in the ith row and j column. And zeros everywhere else. So, even more simple than the identity matrix, right? But not more simple than the zero matrix, right? Zero matrix is impossible. Sorry. And zeros elsewhere. Right? So what we can actually do is we can actually sort of be a bit more specific about this. In general, the ijth entry of capital E subscript capital I capital J is given by this product here. So delta, so this is the Kronecker delta, right, from the last video. So if you're not familiar with that, go and watch it again. So Kronecker delta, capital I lowercase I, multiplied by the Kronecker delta, capital J lowercase j. Right? And the reason why is because this will only ever return 1, right, if I is equal to capital I and j is equal to capital J. In every other scenario, right, it will return 0, right? Because effectively these two things here are not equal, right? So these two numbers here, capital J and lowercase j, they're not equal, right? And what that means is just that by definition of the Kronecker delta, you get 0, right? So it doesn't even matter what's happening here, right? If I was equal to capital I and j was not equal to capital J, you just get 0 times 1, right? Okay, so it's just 0. Okay, so it's going to be 0 all the time except for this one special case, right? Where I is equal to capital I and j is equal to capital J. In which case you get 1 times 1, which is 1, right? So effectively, every entry, you can use this definition to show that every entry of capital E, capital I, subscript capital I, capital J will be 0 except for the one in the ith row in the j column, capital I, capital J, right? So there we go. So that's just the definition of this special matrix, okay? And the special matrix because we can use it to prove something, which is quite cool, okay? And probably for more reasons than just that, right? Okay. So if we vary capital I and capital J, right, effectively between 1 and lowercase m and 1 and lowercase n, right, so if we just sort of imagine all possible capital E subscript capital I capital J for a given m and n, right, so all possibilities of this matrix, right, so for example, if m was equal to 2, n was equal to 2, then all possibilities would be 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. These are all the possibilities, right, for basically the capital E subscript capital I capital J for m is equal to 2, n is equal to 2. Right? So these matrices, they actually form what we call the standard basis. Okay? So these matrices form the standard basis. Form the standard basis, okay, for this sort of set of m by n matrices. Okay? So if I was considering the set of 2 by 2 matrices, then those 4 matrices up here that I'm just sort of drawn out form what we call the standard basis for that set, effectively. Okay? So this is just a definition for now, but it'll come into play later on as well. Okay, so just be familiar with it, and yeah, that's pretty much that. So one final theorem is what I want to prove before we finish off. Okay, because that finishes the chapter, and this is probably the most interesting theorem. Okay, so effectively, what this theorem says is it says, well, first of all, let A be a square matrix, right, such that effectively capital A, capital M is equal to capital M, capital A. But it's not equal to the identity matrix, right? So it's not necessarily like the inverse of M, okay? It's just that we have this sort of commutativity of matrix multiplication there. Okay, so we're imagining a matrix A that basically commutes with this matrix M. Okay, but now we're going to make that even stronger. We're going to say for all square matrices M. So for all square matrices. So right. So effectively, what we're asking is we're asking of A. We're asking quite a lot of A here, right? We're asking that A first of all commutes, which is not always true, right? So that in itself is restrictive. Okay, with a matrix M, but not only a matrix M, all square matrices M. Every possible matrix. It commutes with every possible matrix, right? So you would imagine that would be quite restrictive. And because it's so restrictive, we can actually sort of prove that it will take a general shape. The structure of that matrix will be specific, right? So then the matrix A must actually be equal to, okay, lambda times the n by n identity matrix for any real number lambda that you care about. So there's still infinitely many, right? Because you can just vary lambda, like very slightly, 0.01, 0.02, and that gives you infinitely many matrices A, okay? But even though there's infinitely many, it's still very restrictive, right? It's so restrictive that we're able to sort of categorize these matrices, okay? For some real number lambda, or we're able to effectively identify them, okay? So this is what we need to prove, and then after we prove that, we're done. Right, so first things first, since A obviously commutes with all square matrices, right, it must also commute with each of the sort of n by n standard basis matrices, right? So if, for example, if n was 2, then it must commute with all of these matrices up here, right? Because A is a 2 by 2 matrix that effectively would have to commute with all of these 4 matrices up here. Okay, so that has to be true. Okay, because it has to be true, specifically because it commutes with all square matrices M. Okay? And obviously all square matrices M of the same size, effectively, as A, right? Because obviously you wouldn't be able to do a 2 by 2 multiplied by 3 by 3. Okay, that's pretty obvious, but just also to make that clear. So if A commutes with all square matrices M, obviously A is a square matrix, then it must also commute with the standard basis matrices. Okay, so A must commute with the standard basis matrices, the n by n standard basis matrices, or sometimes you might see that written as n squared standard basis. It means the same thing. Okay, so effectively, what that means is that the ijth entry of this sort of matrix product here, so capital E is just one of those standard basis matrices, capital E, lowercase, capital I, capital J, is equal to, right, equals, effectively, the ijth entry of the other way around, right, of capital E, capital I, capital J, multiplied by capital A, right? So now what we need to do is we need to basically write out what is the ijth entry of this, right? Well, we can do that. AE, capital I, capital J, the ijth entry of that is simply going to be, by definition, the sum, right, from k equals 1 to n of effectively aik, right, delta capital I, k, delta capital J, J. Okay, so this is why, again, you should be really confident with this definition of matrix multiplication, because it's very useful. Okay, and in this case, obviously, the first matrix that appears is capital A. Okay, so effectively, we put the aik first, right? So A comes before like the sort of capital E, right? And then we put capital E second, and obviously capital E ij is defined by delta capital I lowercase I, delta capital J lowercase j. Okay, and obviously we also sum to n, right? Because A is n by n, so that's second, and E is also going to be n by n, right? Because they're both square matrices. Okay, so that those values of n are the same, and they're the upper bound of our sum. Yeah. So this is basically just the ijth effectively component of this matrix product, right? It's just given by this formula, right? Because this is effectively just the definition of matrix multiplication. And if you want it to be, if you're still confused about that, because I know it's a little bit much, effectively just think about it like this, right? In general, it's just equal to this. So it's going to be E ij, and then the sort of kjth sort of element in this matrix, right? And by definition, the kjth element in this matrix is just this. Okay, so that's how we got to it. But you need to be confident with the definition of matrix multiplication. If you're not confident with that, please go back to it, because it's going to be very confusing. Okay, it probably is still confusing, but like you need to just, unfortunately, you need to just sort of, well, not unfortunately, I think it's good. Like, you know, you should struggle with some of these, but yeah, you know, it's difficult, right? So yeah, but hopefully you can see that like that's true, right? Via just the definition of matrix multiplication, right? And by the sifting property of the Kronecker delta, we can see, obviously, that now this thing is not changing, right? Okay, so this is always going to be the same. We can basically just pull it out of the sum. And then we really care about this, okay? Now, by the sifting property of the Kronecker delta, obviously, this is only going to be, it's going to be 0 most of the time, right? But it's only ever going to be 1 in one case. And that is when k is equal to capital I, okay? So this is actually going to be equal to a, lowercase I, capital I, multiplied by delta, capital J, lowercase j, okay? So that is what the ijth component of capital A multiplied by capital E lowercase I lowercase capital J. No, sorry, what lowercase capital I? I mean, capital E sub ij is effectively subscript ij. Capital I, capital J, is equal to. That's the ijth component of that resultant matrix. Okay, and similarly, we can just effectively calculate the ijth component of the effectively the opposite of that multiplication. So that multiplication flip. The ijth component is just given by this sum again. So from k is equal to 1 to n, this time the other way around though, right? So it's going to be delta capital I lowercase I delta capital J lowercase k, right? And then a kj. Okay, because of course this time we want the ikth component of the sort of E matrix, capital E, and the kjth component of the A matrix, okay? And then by definition of matrix multiplication, you effectively scale them. Hello? Okay. And effectively, by the same sort of sifting property that we covered like yesterday, you can see that effectively when k is equal to capital J, then this becomes 1. And effectively, in all other cases, right, because this is constant, so you can pull this out of the sum, right? And then the other delta obviously is not constant, but it'll only ever be 1 when k is equal to capital J. So in general, by the sifting property of the Kronecker delta, that is just simply equal to delta capital I lowercase I times A capital J lowercase j. Okay, that is just that's just the ij component of that matrix. Okay, now these need to be equal because we know that matrix multiplication in this case is going to be commutative, right? So we set these two things equal to each other, right? And that basically gives us some interesting stuff, right? So when we get A lowercase I capital I delta capital J lowercase j is equal to delta capital I lowercase I A capital J lowercase j, right? So this is the defining condition that we're going to use. Okay, and so now what we can do is we can just choose specific values of I and j, right? So I and j is going to be obviously the sort of component, the ij component of our resultant matrix, right? Or I guess it doesn't even necessarily need to be of our resultant matrix if we take capital I. I mean, you'll see what I'm trying to say. But effectively, if we let lowercase I, right, so we can just choose values of lowercase I and lowercase j that we want, right? So if lowercase I is not equal to lowercase j and capital I effectively is equal to capital J is equal to lowercase I, then what do you get, right? Then effectively what you get is, well, this left-hand side obviously becomes 0 because capital J, you get delta capital J lowercase I, right? No, sorry, you get delta lowercase I lowercase j, and I is not equal to j, so then that delta becomes 0. So you get 0 is equal to delta I, so that's just 1, multiplied by a ij, right? So in this case, what you see is that a ij is simply going to be equal to 0. So the ijth component of our matrix capital A will be 0 as long as I is not equal to j, right? And if you're wondering, what are we doing here and why that doesn't restrict anything, because obviously we know that it has to commute with all of the elementary, effectively all of those matrices that, like for example, if it was 2 by 2, has to commute with all of these 4 matrices, right? And because it has to commute with all of those 4 matrices, I mean, we don't necessarily need to use all of them. We just consider specific cases of those matrices where capital I is equal to capital J is equal to lowercase I, right? We're just considering specific forms of those matrices that effectively allows us to simplify this, right? Because we know it commutes with all of them, but we don't necessarily care that it commutes with all of them. We just use some of them to show this, right? And because this being true sometimes is enough for it to be true always, right? Because it's restrictive, right? Because if this wasn't true, then it wouldn't commute with all square matrices, right? So effectively, all non-diagonal elements of A, non-diagonal elements of A are equal to 0. Okay, so that's already very, very good. Okay, because that's like, we're trying to prove that it's lambda times the identity matrix, so already that's very good because the identity matrix has 1s in the diagonal, which we haven't rooted out, right? And it has 0s elsewhere, which we're seeing here, right? And then if we consider some other special sort of matrices that we multiplying it by that are of the form capital E lowercase capital I capital J, then if capital I is equal to lowercase I and capital J is equal to lowercase j, then effectively 1 becomes, did I write it as 1 in this case? I didn't write it as 1, but effectively I'm talking about this. That's what I wrote in my notes. Then 1 effectively just becomes a lowercase I delta effectively lowercase j. So that's 1, and that's equal to delta lowercase I a ij. No, sorry, a jj. Sorry, a jj. Right. And so what this effectively implies that a lowercase I is equal to a lowercase j. A lowercase j. Okay, this is true whether or not I and j are equal to each other, right? Lowercase I, lowercase j are equal to each other, right? I mean, obviously, if they are equal to each other, then it's very trivial, right? Because you're just representing the exact same element, right? If they're not equal to each other, this is also true, right? So effectively, what this is telling us is that all elements on the diagonal, right, are equal to each other, effectively. So all elements on diagonal are equal to each other, right? So this has to be true always for A, because if A, this is effectively a condition for A to commute with these specific matrices. This needs to be true. Okay, so capital A must always have this property, and because they're equal to each other, we can call them lambda. Call them lambda, right? So we'll call this shared value that they all have lambda, right? Because they're equal to each other, so we'll just call them lambda, right? They could all be 2, could all be 5. There's no restriction on that, right? It's just lambda, right? So because all the elements in the diagonal look at lambda and everywhere else is 0, we have a matrix that looks like this, right? So we're going to have, sorry, not 0. We're going to have lambda 0, 0, bunch of zeros, however long. It's going to be n by n as well, right? Remember that, n by n. And we're also going to have 0, lambda 0, so on and so forth, until at the end you get 0, 0, all the way up to lambda at the end, right? So we can pull out a factor of lambda, you just get the identity matrix, right? So effectively, we have now enough information to make our conclusion, right? So capital A must be of the form lambda times the n by n identity matrix, right? Which is wonderful, right? So if there is a matrix, a square matrix that commutes with all other square matrices that obviously it's allowed to, then it must be of this form, lambda times the n by n identity matrix. Really, really, really nice. Okay, equivalently also, it must take this form, but also all matrices of this form will indeed commute with every other every other square matrix that obviously they're allowed to. Okay, and so there's no more restrictions that we need to make. Okay, we were restrictive enough. Okay, because we could have we showed that it has to take this form, but there could have been special cases where it takes this form but doesn't work. But actually, all of the cases where it takes this form work. So we're done. Okay, and we've actually we've shown we wanted to. Yeah, I mean we actually showed more than we wanted to, right? At the end there, right? We didn't really show it, but it's pretty trivial to note that for all values of lambda, for all like possible versions of this A, they will indeed commute with square matrices, because the identity matrix, they effectively multiply by any other matrix, just gives you the other matrix. And then obviously we scale that by lambda, but if you do the other way around, it'll also be scaled up by lambda, because it's the scalar constant. So it's pretty easy to note that. So I don't like to use the word trivial, but I guess if you follow it, then it is. Okay, but yeah, that's pretty much it for today. That last proof is very difficult. If you are unsure about anything, I would highly recommend that you go to these lecture notes here. Okay, they are really, really good. I've got pretty much everything I said in this video from them, and this is the proof that I just basically spoke about. Okay, and it looks very short here, but it's quite complicated and quite dense, and it's quite a difficult proof. Okay, so you need to be competent with it. We don't necessarily need to be competent with it, but obviously, if you want to really, it's a math. At the end of the day, this is the first year maths course, right? So hopefully you want to understand these sorts of things. Okay, and it's probably going to help you later on in terms of like you have to obviously write proofs and things like that, and construct proofs in terms of like seeing how they work and following proofs in general, right? Because that can be quite tricky. Okay, and this is a tricky proof. All right, anyway, see you guys in the next one. Thank you guys for coming. Or if you've watched the whole video, thank you very much. I very much appreciate that. Until next time, I'll see you guys. Goodbye.